Hi, this is an example problem on quantum mechanical hydrogen atom. This is how quantum mechanics understands the hydrogen atom. This one says the total energy of the electron in a hydrogen atom is minus 0.278 eV. In part A, we're asked what is the maximum value for the magnitude of the orbital angular momentum of the electron. Part B is what is the minimum value for the magnitude of the orbital angular momentum of the electron. And part C, we're looking for the greatest and second greatest possible values of the z component of the orbital angular momentum of the electron. So all of these things, angular momentum magnitude, z component, these are related to the quantum numbers. And this value here for the energy, that's also related to the quantum numbers. In fact, that's n, the principal quantum number. Let's look at some notes for the hydrogen atom. Notice that the hydrogen atom, the energy equation depends on the principal quantum number exactly the same way as it did for the Bohr model. Bohr got that part right. If we look at the other quantum numbers, we can see that L, capital L, that's what the angular momentum is. It's quantized. It can only have discrete values, and that depends on little l, which is the orbital quantum number. And L sub z, capital L sub z, that's the z component of the angular momentum. That's quantized as well, and it's quantized based on multiples of h over 2 pi multiplied by little m sub l, the magnetic quantum number. Now remember that n is the topmost in the hierarchy of quantum numbers, the principal quantum number n. It determines the possible values of L, and L determines the possible values of m sub l. So we need to remember again this hierarchy of what possible values lower down are allowed based on the values higher up here. So first thing we should do in this problem is figure out what is the value of n, because that's going to determine the max values for these other quantum numbers. We're given the total energy, we can use Bohr's equation. So we remember Bohr's equation. It is equal to En is minus 13.6 eV divided by n squared for hydrogen. Now, we know the energy. Let's solve for n. So we can write this as n squared equals minus 13.6 eV divided by En. And in this case, we're looking at n squared. We can go ahead and take the square root of both sides. So n is equal to square root of minus 13.6 eV divided by negative 0.278 eV. We know the energy. We're going to figure out what the n value that corresponds to it is. I get a value of about 6.994. Now remember that n itself can only be integer values, right? So this really must be n equals 7, right? All right, now that we know what the value of n, we can start to figure out some of these other things like in part A. Let's go ahead and drop this down here for a second. So part A asks, what is the maximum value for the magnitude of the orbital angular momentum of the electron? Let's look the equation up for that. Orbital quantum number, orbital angular momentum. Here it is, L equals H LL plus 1. I'll go ahead and copy that real quick. So there's our equation. And notice, though, it depends on the value of L. So the question is, n equals 7, what possible values of L can we have? Well, we want the biggest possible value of L because we want this to be as large as possible, right? So let's go back and look and see, enumerating the quantum states. So here we know that n, that is equal to 7. What are the possible values of L? Well, we can go up to 7 minus 1. We can go up to 6, right? All the way up to 6. And then we got to stop there. Can't go up to above n minus 1. Well, 6 is going to be the biggest value of L. That's going to be the value that maximizes the angular momentum, the magnitude capital L. So let's go ahead and put that in there. L equals 6. Max allowed, since n equals 7. And let's put in our values here. Let's look up Planck's constant H. It's right here. Now, we've been using this version, EV times seconds, a lot with the energy formula. But for these ones down here, L, angular momentum magnitude, Z, component of angular momentum, we want to use the ordinary joules times second, 6.626 times 10 to the minus 34th to be in SI units. There we go. And the rest we know. Divide that by 2 pi and multiply by the square root of 6 times 6 plus 1. Putting that into the calculator, we get 6.83 times 10 to the minus 34th. And let's see what our units are. We've got joules times seconds, right? Remember that a joule is a kilogram meter squared per second squared times a second. That's going to give us a kilogram meter squared per second. These are the standard units for angular momentum. And now we know why the number is so small. We're using the standard units of angular momentum, which are developed for large things. But this is for an electron. The magnitude of the electron's angular momentum in this particular state of the hydrogen atom, where n is 7, L is 6. That's the greatest you can have for the n equals 7 shell. All right, let's look at part B. What is the minimum value for the magnitude of the orbital angular momentum of the electron? Well, we want to get the smallest value of L now. We got n equals 7. Let's go back and look. We could choose 0. That's the smallest value of little l. All right, so now when we put L equals 0 into the equation here, little l equals 0, we get the smallest value of capital L. Well, once that's 0, then the whole thing's going to be 0. There's your min value, and this was your max value. All right, let's look at part C. If the value in A is the actual value, so this value right here, the max value, we're going to use this one for part C. What are the greatest and second greatest possible values for the magnitude of the Z component of the orbital angular momentum of the electron? Well, for part C, the Z component of the orbital angular momentum, that depends on the quantum number m sub L. And let's look at those equations. So here is the formula for L sub Z as a function of m sub L. So we're going to need to figure out the greatest and second greatest values of capital L sub Z. Well, we're going to need the greatest and second greatest values of m sub L here. Let's look and see what they are. We know in this case that L is 6. Let's see what m sub L can be. So when L is equal to 6, we can get a bunch of values for m sub L. It's going to range from minus 6, going up by 1 each time, etc., all the way up to plus 5, plus 6. So these are going to be our two biggest values for m sub L. And when we go back here, so we can use the greatest That's going to be when m sub l is equal to 6. Planck's constant. Again, I got to use the standard SI units here, since this is our angular momentum. And then divide by 2 pi. That gives us a value of 6.33 times 10 to the minus 34th kilograms meters squared per second. And for the second greatest value of the capital L sub z, the z component of the angular momentum, that would be for the orbital where m sub l is equal to 5. In this case, it would be equal to, same equation. Now we just, instead of 6, we put in a 5. And that comes out to 5.27 times 10 to the minus 34th kilograms meters squared per second. And so now you can see how to solve these problems here that were properties of the electron, its angular momentum, magnitude, z component, and energy depend on the quantum numbers of the state.